Hello, my name is Sadie Allen, and I am a senior undergraduate student in Boston University's Performance and Energy Aware Computing Lab. Today I will be presenting my research on version detection for software discovery in the cloud. Cloud systems can contain millions of virtual machines, which can in turn be accessed by millions of individual users with different goals. Current trends in cloud computing, such as continuous integration and delivery of software, and a shift towards open source instead of vendor-supplied proprietary software, means that there's much more diversity in the components found on a system. With this comes the problem of keeping track of the contents of a multitude of VMs and containers in the cloud. One solution to this problem is to employ software discovery methods, which continuously identify software present on a given system in order to verify its compliance, security, and efficiency. Version detection and software discovery is vital for rapid location and patching of vulnerabilities. If a vulnerability is reported in a certain application, system administrators would ideally know not only if the application is installed, but also if the vulnerable version is installed in a particular VM or container in order to avoid wasting time patching unaffected or irrelevant systems. Version detection allows for problematic software to be pinpointed more quickly, which limits the window of time during which a system is vulnerable. Our lab's previous work on software discovery, a tool called Praxi, serves as the basis of comparison for our study, as well as an important building block for our novel algorithms. Broadly, Praxi uses records of file system changes to predict software installations. Praxi trains with change sets, which are records of all file system changes during a certain time interval. They contain the full paths for all files created, modified, and deleted. For our research into software discovery, they are recorded during specific software installations and labeled with the name of that software. Next, Praxi uses a tool called Columbus to generate tag sets. File paths are tokenized to get a list of directory and file names, and these tokens are then indexed into a frequency tree to discover tags. Tags are defined as the most frequent, longest common prefix among the list of all tokens in the file system tree. Praxi then generates a trained classifier using the ML engine VowPal-Wabbit, or VW. Tag sets are treated as bags of words, and VW generates a single multi-class classifier for all single labeled change sets in the corpus. During testing, Praxi predicts the application name for unlabeled tag sets. In my research, I had two main goals. The first was to evaluate our original Praxi method on version detection tasks, and the second was to devise novel algorithms that could perform better than Praxi. The following key insights informed the development of new algorithms for version detection. First, we realized that Praxi would likely struggle to identify specific application versions, since change sets for two versions of one application could look very similar. This means that the tag sets would also end up looking extremely similar, so it would be difficult for VW to distinguish between them. Our second observation was that Praxi may benefit from the generality of passing in multiple versions as examples for a specific application. From these observations, we decided to implement variations of the original Praxi algorithm that use Praxi to identify a change sets application, and then employ file path-based rules to differentiate between specific versions of that application. Here's a diagram of the training and testing workflow for our novel algorithms. Change sets are passed in during training such that the VW classifier is trained only using the application label. Both version and application labels are passed to the rule generation module, but rules need only differentiate between different versions of a single application, not between all versions of all applications. When developing rules for version detection, we knew a good rule should be unique, that is, apply only to one version of an application, and ubiquitous, applying to every example of a given version. We implemented two rule generation methods, basic rules and combination rules, described in the following slides. Basic rules assume that every version of an application has at least one file that is unique to it and appears in every change set example. This is achieved by taking the union of all change sets of a specific version to get the set of all file paths that appear in any example of a given application version. The next step is finding any overlap between the unions of different versions. Any file path appearing in more than one of the unions cannot function as a rule. Once the overlap is determined, it is removed from every change set. Finally, the intersection of all the change sets for a version is found, and all of the file paths in that intersection are the rules for that version. The major drawback of this method is that if a version does not have any unique and ubiquitous files, no rules will be generated and the version will not be identified during testing. In the combo rules implementation, a series of dictionaries are used to create more sophisticated rules compared to those generated by the basic rule algorithm. Specifically, a file path can be used to differentiate between two versions, and the absence of a file can be used as a rule. The three different types of rules that can be created for a given version are shown to the right on the right of the slide. Unique to rules are like the rules generated by the basic rule algorithm. The remaining two rule types allow the presence of a specific file to differentiate between two version labels. The output of the combo rule generation script is a dictionary mapping version labels to sets of rules, which are used to make version classification decisions in the evaluation phase. We also attempted to mitigate the issue of versions of the same application having similar file paths by attending file sizes to the ends of file paths listed in the change sets. We evaluate this change in our basic and combo rule generation algorithms and compare the classification accuracy to that of our original methods. We chose the pool of applications for our version detection experiments from the Ubuntu Popularity Contest, which maps the usage of all Ubuntu packages. Change sets were recorded from the top non-library, non-graphical packages. We exclude applications that do not have at least two versions across 3 Ubuntu releases, Ubuntu 14 LTS, Ubuntu 16 LTS, and Ubuntu 18 LTS. We recorded 50 change sets for each version of each application, which resulted in a total of 14,050 change sets in the entire data set. We ran classification experiments individually for each of the 5 algorithms: Praxi, basic rule-based, combo rule-based, and basic and combo rule-based with added file size information. Each experiment was performed with tenfold class balance cross-validation. In our experiments, we found that Praxi was able to detect specific versions of our applications with relatively high accuracy, achieving an F1 score of 0.941. As evident from the flow diagram in the bottom left of this slide, all but one of Praxi's errors were in telling specific versions apart. It only misclassified the application name once throughout the entire experiment, but confused versions in over 800 instances. The rule-based algorithms without file size information fared the worst in the experiments. We expected this low accuracy as different versions of the same application would share most, if not all, of their file names, making their change sets difficult to distinguish. We see a significant jump in classification accuracy with the addition of file size information to the rule-based algorithms. The basic method achieves an F1 score of 0.999, misclassifying just 5 change sets in the entire experiment, and the combo method achieved an F1 score of 0.983. This means the extra information provided by the file sizes is enough for the basic rule-based algorithm to create rules for virtually every version of every application. The combo rule class performs worse than the basic rule class with the addition of file size because the combo rules have a probabilistic nature. In order to be classified as a specific version, an application must satisfy a certain proportion of the rules generated for that version in the training phase. This is unnecessary when there are unique and ubiquitous rules for every application and version that could be used instead. Although Praxi does not yield the best accuracy of the algorithms that we tested, it is the best in terms of running time, as the other methods that we tested ran 5.2 times slower. This is unsurprising, as the rule-based methods add an extra step in both the training and evaluation phase. More experiments regarding how the running time overhead scales are necessary to understand the extent to which our rule-based methods are worse. To show the value of version detection in cloud software discovery, we sought to demonstrate its functionality in a situation with a real known vulnerability. We tested whether Praxi and the basic rule-based algorithm with file size could identify one of the versions of OpenSSL with the heartbleed bug. For these experiments, we recorded 30 change sets of 2 versions of OpenSSL, version 101B, which has the vulnerability, and 111D, which has the patch. We then chose 5 other applications from the main experiments at random and added all of their versions to the corpus to show that Praxi could accurately distinguish the OpenSSL application from other applications. We ran experiments with tenfold cross-validation. In this case study, Praxi achieved an F1 score of 0.936, while the basic rule-based algorithm with file size had an F1 score of 0.999. This demonstrates that the algorithms can successfully identify a vulnerable application version. Through our experiments, we demonstrated the ability to perform version-specific software discovery for cloud systems. We tested an existing software discovery algorithm and propose novel methods involving auto-generated rules used to distinguish between versions of an application, achieving up to 99% accuracy. We also demonstrated a real-world situation in which version detection would be useful with our OpenSSL case study. There are many avenues for future work our group is exploring. Of chief importance is the development of the software architecture necessary to implement Praxi and version detection methods on real systems using containers as they become more popular. The ideal architecture will be able to actively monitor the applications present on a given cloud system and alert administrators if the user installs an unwanted application. Cutting down the running time of our software discovery algorithms is vitally important if we hope to achieve this constant monitoring. One major open problem in our work is determining potential ways to cut down the running time of our novel rule-based algorithms. Another useful extension of this project would be to connect it to the National Vulnerability Database to stay up to date on potential vulnerabilities. We welcome any critique concerning how to further increase the applicability and utility of our method in modern cloud systems. Thank you for listening, and I look forward to hearing your questions.